Okay, are you ready to do some coloring on your notes today? Yes. Okay, so a couple of quick things. The AVID deadline for the scholarship, okay, listen, your AVID deadline is tomorrow. So if you're in AVID, I don't know why I haven't, maybe just most of y'all aren't in AVID, but most everybody in AVID gets that, so you should apply for it. Okay, then the normal BHS non-AVID scholarship to not have to pay the whole $64 is due January 25th. Okay, also that random list of scholarships I sent you, just generic scholarships, those are due February 1st. Okay, are you guys getting on total registration and registering? Okay, we already talked. The money is due February 18th, and then after that you have a late fee. So February 18th.
Is it not like the 3 days? Like you pay like, or it's just all you have to pay on the 18th?
It all has to be due the 18th, but you can turn in some each week to go towards it. Now, one more thing, guys. Okay, the reason that the scholarships are due in January is so that they can tell you whether or not you get the scholarship before you pay. So I wouldn't, like someone in my second period was like, well, I already paid the whole thing. What if I get a scholarship? I don't know. But I would say don't pay until you know if you got it or not. So you pay the correct amount versus having to wait for a refund. Okay? Great. All right, so here's what a Riemann sum is. Okay, this is a method of estimating the area for a non-geometric function. Okay? Riemann sums is a method of estimating the area for a function if it doesn't make a perfect geometric shape. So like in your homework 3, all of the things were a triangle or a trapezoid or a rectangle or a semicircle. Okay, that's not how most functions look. So we need other methods to find those areas. So if you will please draw for me a function going uphill. So just an increasing function. Okay? Then we're going to put A here and B here. Now, if I asked you to integrate from A to B of f of x dx, what does that stand for in the picture? We were finding it on Monday. And you already wrote it on your paper. The area. Very good. That is the exact area between f of x and the x-axis on A to B. So if I wanted to find the integral of the graph that I just drew, then I would start here at A, and then I would shade all the way over until I get to B. Okay, so that is my integral's exact value. But then you'll notice that's not a geometry shape. So I can't use pi r squared or 1/2 base times height, right? So here's how you do a Riemann sum. We're going to draw it several times, and then we'll, when we switch to the classwork, not be drawing as much. So what I want you to do is take your A to B. I want you to cut it in half. And then I want you to cut each of those halves in half. So you should have 4 parts. Good? Okay, what I want you to do is the first one that we're going to draw is going to be a left Riemann sum. Okay? This is a left Riemann sum. Here's what you do. You're going to take your graph and you're going to draw in little division lines to divide it into 4 parts. Then, for each of those parts, you're going to take the left y value and you're going to make a rectangle. So out of these 2 points, notice this is my endpoint 1, this is my endpoint 2. I'm going to use the one on the left. And then I would find the area of that rectangle. Okay, now let's go to my second one. These are my 2 choices, here or here. I'm going to use the one on the left. So cut across, draw in your rectangle 2. Okay, then from here to here, I'm going to pick the left one. And then from here to here, I'm going to pick the left one. And then what I'm going to do is, I'm going to take the area of all 4 of those rectangles, and I'm going to say, okay, well, my integral is about that. Now, is it a perfect estimation? No. Okay, now, overall, will my rectangles be a little too big or a little too small? Rectangles will be a little too small, right? Because I have all these extra pieces that didn't get counted. Okay, now here's what you would do for your estimation. So I'm going to put integral a to b of f of x dx is approximated by, so little squiggly equals, and then you would add the area of rectangle 1, rectangle 2, rectangle 3, and rectangle 4. Now here's how you would find each of those areas. You would do base times height, right? Your base we're going to call delta x. So each of these would be your base. So I'm going to put delta x equals the width. And then you're going to multiply by the y values on your thing. So I'm going to call this one y1, y2, y3, y4, and then this one is y5. Now, for that first rectangle, I use the left endpoint. Will I use y1 or y2 as the height of the rectangle? For this rectangle right here, which one did we use? y1. Plus, for my next rectangle, I'd put however wide it is, I'm just going to call it delta x, and then I would multiply by the left endpoint of this rectangle, which is y2. Okay, plus, my next one would be delta x times, and then I want to use, for this third rectangle, okay, it would be y3. And then for my last rectangle, what's my left y value? y4. Now, I want you to notice which y value never got used. y5. There is another type of Riemann sum where you're going to use the right side. So we're going to do that one next. So come down here. I want you to try as close to the same. Yes? Okay. So I'm going to put as a little star here, last y value never got used. Okay? Now what we're going to try to do is draw the same picture again, but now we're going to do what's called a right Riemann sum. Okay, so same picture going up. We're going to put our A and our B mostly in the same spot. I'm going to shade my exact area. So from here to here, I want the exact area between the graph and the x-axis. And then I'm going to split my graph up into pieces, just like we did on the other one. Cut it in half, then cut those in half. Then draw your lines in vertically so that you're slicing your graph up into pieces. But then instead of choosing, let's label these as well, y1, y2, y3, y4, and y5. But instead of using the left endpoint on each subinterval, for a right endpoint, you would use the right side. Okay, so I'm going to label this right Riemann sum. Okay, so look at mine first, unless you are pretty confident you've got it. For this first one, which y value am I going to pick as the height? Y1 or Y2? Y2 is on the right. Okay, then for my next one, am I going to choose for the height Y2 or Y3?
So it's just the first one.
The first one doesn't get used, exactly right. Okay, then Y4, and then Y5. Okay, and then each of those areas of those rectangles, you would compute a sum. That's why it's a Riemann sum. Okay, and that would be an estimation of your area. So I'm going to put here the integral from a to b, f of x dx is approximated by, and then we're going to go one rectangle at a time. For this first one, I'm going to call it A1. What is my width? We'll call it delta x. And then which y value did we use for our height? Y1 or Y2? Y2 plus. Then for my next one, it'd be delta x times Y3. Then for my next one, it would be delta x times Y4. And then for my last one, it would be delta x times Y5. And then I'm going to put a little note, in case you didn't hear Sean say it, your first y value never got used. Okay? Now, there's one other thing that I want to talk about when we're doing these graphs. You can always tell if your graph is going to be over or under based on two things: which direction your graph is going and which endpoint you used. So if I'm looking at my first graph here, okay, I'm going to put the Riemann sum is less than the actual area because f is increasing, so the left endpoint is the smallest on each subinterval. Okay, so a left Riemann sum is less than the actual area because since f is increasing, your left endpoint is smaller than the rest of the graph on that chunk. Okay, now let's write the same sentence now, but down for this one. So after you write it down, I want you to think about for my right Riemann sum. Are my rectangles too big or too small in the right Riemann sum? They're too big. So I'm going to put my Riemann sum, I'm going to abbreviate that RS, is greater than actual area because f is increasing and the right endpoint is the biggest. On each subinterval. Now, we're not going to write this over and over again. I just want you to have a good explanation in your notes so that as we get closer to your tests and stuff, you have something to look at. Okay? Now, I want you to think about, is it only left or right that matters? If my graph was going the other way, let's say that my graph instead of increasing was decreasing. Think about a right Riemann sum. Would it still be too big if the graph was decreasing? Okay, it would be too small. Now I'm going to draw a picture of that one, just sketch it really quick, and then we're going to go on to the last type. So on here, I want you to draw the same picture, but this time going down. And we're just going to quick sketch it. Okay, so my graph A is here, B is here, cut it up into 4 rectangles, and then draw in your right Riemann sum for that one. Okay, and you're going to notice that your actual area is being underestimated by your right rectangles. They're too small. So it's not just left or right. You have to think left or right on an increasing or a decreasing function. You have to know both things to be able to tell. Okay, so I'm going to put a little star here and put a right Riemann sum is an underestimate if f is decreasing. Okay? So basically it's just backwards. And I wouldn't memorize those. I would just sketch a quick pic, look and see which way it's going, and then you're good. Okay, so take a look at your classwork for me. Okay, we're not going to run through all of this, but we're going to do some of them. Okay, so the first thing that I want you to do on your first question is sketch a graph. Okay, don't be super extra and put a bunch of markers on the y-axis. Okay, we're just going to sketch a graph. So, here we go. Good. Okay, so label your x-axis 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6. And then I want you to put your dots so that they're going the right direction. They're either going up or down. How are they going on that table? Down. So 0, 1, 5, 6. Okay, and then I'm going to make my dots going down. So 22, 17, 13, 10, 7, 5, 2. Okay, good enough. Now, on the R of t, okay, and then here we have time. Okay, the first thing that we're going to do is cover what we talked about yesterday, which is units. So I'm going to read through it for you, and then we're going to think about what is being measured in our integral. So it says, coal gas is produced at a gas works. Pollutants in the gas are removed by scrubbers, which become less and less efficient as time goes on. R of t represents the rate that the scrubbers are removing pollutants during production, measured in tons per month. So this is how well the scrubbers are working. Okay, and notice it's going down. Okay, then it says the table below shows values of R of t at the start of each month. Okay, so if I wanted to find the integral from 0 to 6, do you remember yesterday we said if it's length times width, what do you do with your units? You multiply them. So if I do tons per month, which is like my height, times months, which is like my width, what do I get as my units? Only tons. Very good. It's tons per month times months. Your months are going to cross out, and you just get the number of tons left over. So this integral represents the number of tons of pollution or pollutants removed by the scrubbers, and then over what time period? What is my integral boundaries? 0 to 6. What is that measured in? Months, right? Okay. So remember that if it's an interpret, you should be multiplying the units because that's how you find area. It's just base times height. Okay, so now let's do it for our problem. Ready? So for a left Riemann sum, okay, let's sketch our little graph here. Okay, divide it up. For my left Riemann sum, for my first rectangle, which y value am I going to pick? 22 or 17 if I want the one on the left? 22. Good. So now what's my width from 0 to 1 here? From 0 to 1, how far is that? 1. So integral 0 to 6 R of t estimated by, and then remember every time it's a delta x times a y value. So for this one, my delta x is 1 unit across and my height is 22 plus. Okay, now we're going to this one I'm highlighting in green here. I want my left rectangle's area. How wide is it? from 1 to 2, how wide is that? 1. And then my left endpoint, would I pick 17 or 13?
Why did you do 1? Oh, that's just the width.
Because that's the width, correct. This is my delta x. Okay, would I use 17 or 13 for my green rectangle? Okay, 17 plus. Okay, next I'm doing my pink rectangle. Okay, I'm using the left endpoint across. My left endpoint is a 13, my right endpoint is a 10. Which one am I using? 1 times 13 plus. Okay, then for my next one, I'll do it in yellow. Cut it across. My left endpoint is a 10, my right endpoint is a 7, so I would be using the 10. My next one is a width of 1, my left endpoint is a 7. And then for my last one, okay, this is a 7, this is a 5, this is a 2. Which one would I use on the last one? 5. Now, let me remind you who never got used. 2, because it's the right side on a left endpoint. Now, look at your rectangles. Are they too big or too small? The rectangles are too big. So you would say this is an overestimate. Okay? Alright, now let's do the same thing for a right Riemann sum, but I'm not going to redraw the picture. We're going to just kind of look at the same picture and tell, is your width always going to be 1 again? Yes. But who gets skipped on the right side? Not the last one, the first one. So from here to here, I'd go my width is 1, my height is 17. Plus. For my second rectangle, my width is still 1, but my right endpoint is 13. Okay, now I'm on my pink one. This is rectangle 3. I'd be using a width of 1, but a height of 10. Then 1 times 7, then 1 times 5, then 1 times 2. Okay, and you'll notice that on that right side, your 22 never got used because it was the very first point, and I'm using the second point each time. Okay? Now, imagine on your graph here, I'm going to resketch it real quick. You can do it if you want to. Okay, but if I'm doing a right Riemann sum, how will my rectangles fall? They'll be underestimate of the real area. Okay? So this is a picture of it if it were a right Riemann sum, and I had used the right side each time instead of the left. Okay? So I'm going to label this one as a left, this one as a right. Okay? Good with that? Okay, there's one more type. Go back to your notes. The third type, yes, is a midpoint. Okay, so I'm going to have to turn the page here. The last type is a midpoint Riemann sum. Okay, and here's how it looks. Draw your graph. Make it go uphill still. A is here, B is here. This is the last thing we'll do in your notes. Okay, I'm shading my real area. That's my exact integral. Okay, then I'm going to cut it in half. Then I'm going to cut each of those in half. Divide up your sections. And then for each midpoint sum, what you're going to do is you're still going to have your delta x here. Okay, delta x will still be the width. But instead of choosing one of the sides, you're going to have to choose the y value of the midpoint. So watch me draw it and then you do it. So I'm going to go between would be here, and then I'm going to use that height to draw my rectangle in. Okay, then from here to here, this is the middle. I would do my dot here, draw my rectangle in. This is halfway, I'd go here, draw my rectangle in. And then for the last one, I'd go here and draw my rectangle in. Now, I want you to think about, as you draw it, the over-under question that we've been answering for all the other ones. What do you notice about the rectangles? Yeah, some of them they're above, but then what about this part? They're below, right? So each time your rectangle is a little too big on this side, but then a little bit too small on that side. So that error is going to cancel out. Now, it's not going to cancel out perfectly, but it makes midpoints more accurate. So put your error is a little above and a little below on each subinterval. Okay, so then that makes this a more accurate estimation than a left or a right. Because instead of all of your error being too big or all your error being too small, you have a little bit of both, and those are going to cross out with each other. Okay? So go back to your classwork. We're done with your notes for now. And we're going to do that exact same picture, but we're going to do it as a midpoint. Okay? So on your notes, please. Okay, we're going to sketch our little picture again at the bottom. Okay, so it would be 0, 1, 2, 3, 4, 5, 6. And then I'm going to just make my dots kind of steadily going down, not overthinking any of the y values. Okay, so there's my graph. Oops, I missed that one. Okay, then cut your graph up. Now, actually don't cut your graph up yet. Okay, when I draw in my divisions, I have to make sure that I have a number as a midpoint. So, can I go from 0 to 1 if I don't know the value at a half? No. What I'm going to have to do is, I'm going to have to go from 0 to 2 so that at 1 I can draw my height then. So for a midpoint, you're going to have to skip 1 so that that point can be the middle. Does that make sense? Okay, so from 0 to 2, I have to leave 1 so that it can be the y value in the middle.
Oh, so you did that for the next one?
So for my next one, I'm going to go from 2 to where? 2 till 4. And then what's my y value going to be at? 3. Because then 3 gets to be in the middle. Okay, and then from 4, I'm going to jump till 6. And then I'm going to use 5 because that's in the middle. Okay, now I'm going to write in my ordered pairs for these midpoints because those are the only points that I care about. From 0 to 2, my midpoint was 1, which goes with 17. For my second one, my midpoint was 3, that goes with 10. And then for 5, it was 5, 5. So when I do my area, what is the width of this first rectangle? Is it still only 1? It's 2. So it's going to be delta x times y still, but my width is going to be 2 times 17. Okay, then for my second rectangle, okay, how far is it from 2 to 4? Okay, it's 2 units across. And then I'm going to use the y value at 3, which is 10. And then for my last one, I do 2 times 5. Make sense? Okay, now, I want you to think about, is there a way for me to make this writing shorter? Okay, if the delta x is always 2, could I rewrite it like this? Are those the same? Yes. Now, you can only do that if your delta x is always the same. So I'm going to put a little star here and put, this is a shortcut for equal subintervals. If they're all the same width, then you can be like, okay, these are all going to have a 2, so I'm just going to write it in the front. But if they're different each time, then you cannot do that. Okay? And then for your estimation over under, you would say, I don't know. Okay, nobody knows. We know it's more accurate, but we don't know if it's going to land over or under because those areas are canceling out with each other. Okay? All right, turn the page. Okay, next one. You have a graph already drawn for you. We're going to interpret the meaning first. Okay, it says the rate of fuel consumption in gallons per minute recorded on a plane flight is given. So this is gallons per minute. And then it says it's measured as a function of time, which is measured in minutes. What do I do with my units to find area? I do length times width. So it would be gallons per minute times minutes. What would I get? Gallons. So this represents the number of gallons. Okay, and then it says this is the gallon, the fuel consumption. So the number of gallons consumed over 0 to 90 minutes. Okay? Okay, read through part B. Which endpoint are we going to do for part B? A left or a right? What does this say for part B? Okay, a left. So I'm going to go from here, cut your graph up. So 0 I have, 30, 40, 50, 70, 90. And then each time I'm going to use the left y value to draw in my rectangles. Hi. So it'll be left across, rectangle. Left across, across, across. And then each time, remember, you're going to do the width of the rectangle and then the height of the rectangle. Same thing every time. So for my first big fat rectangle, we'll call this A1. What would the width of A1 be? How wide? 30. And then how tall? 20. So that'd be 30 times 20 plus. Okay, now we're going to our second rectangle. Okay, so that's this little skinny one right here. We'll call it A2. Okay, for A2, how wide is it? 10, because from 30 to 40, so that'd be 10. And then which y value did I use, left or right? I used the left one, which is what? Look at your table. 32. Okay, plus. Now, I want you to start using the table instead of only looking at the graph. So let's look at our first two rectangles. How far is it from 0 to 30? 30. Which endpoint did I use? 20. Then for my second rectangle, from 30 to 40, what was my distance? 10. What was my left endpoint? 32. Okay, now from 40 to 50, how far is that for rectangle 3? 10. And what's my left endpoint? 41. Plus. Next one, from 50 to 70, how far is that? Delta x of 20, and then my left endpoint would be 55. Okay, then my last one, I'm going from 70 to 90. How far is that? 20. And then what is my left endpoint? 65 or 72? 65. And then notice, did I ever use 72? No, but it was a left endpoint, so that's okay. That is a 32, yes, a 10 and then a 32. Okay? Now, look at your graph. Are your rectangles too big or too small? Which one? Too small. So this is an underestimation of the actual area. because your rectangles are a little too small. Okay, skip number 3, turn the page. Skip number 3, turn the page. We're going to jump to the next one. Okay, so right here it says you're on a ship going to Gilligan's Island. The velocity is measured and recorded in the table. Interpret the meaning. Okay, so I have miles per hour. Here I have hours. When I multiply miles per hour times hours, what do I get? Miles. Miles that the ship traveled from when to when? From 7.5 to 9.5. Now that would be what time? 7:30 to 9:30, so that's the same. So you would say this represents the number of miles traveled by the ship over 7.5 to 9.5 hours. Now, if you wanted to put from 7:30 p.m. to 9:30 p.m., that's fine. That's the same thing. Okay, part B. Look for the instructions. They have to tell you what kind of sum to do. Because you have 3 choices, left, right, or middle. Which one are we doing on part B? Okay, it says a midpoint. Now, for a midpoint, do you remember you have to leave something in the middle? So notice it even gives you a hint here that we're going to do 30-minute subintervals. So what would my first 30-minute segment be from when to when? 7:30 to 8. And what would my midpoint value be? 25. Okay, then from 8 till when? 8 to 8:30. What's my middle y value that I would be using? 22. Then from 8:30 to 9, what's my middle y value? 10. And then from 9 to 9:30, what's my middle y value? 26. Now, quick question. Are my delta x's always the same, or are they different? They're always the same. How long? 30 minutes. Now, I can't do it in minutes because we're talking about hours. What would I put as my delta x then? 0.5. Very good, because it has to be in hours. And since it's always 0.5, I'm going to do the pull it out thing, okay? So look, watch. I would put 0.5 in the front, and then I'm only going to list the middle points. So it'd be 25, 22, 10, 26. 25, 22, 10, 26. Now, could you write it out where each one gets their own 0.5? Sure, but you don't have to. Okay, can you tell if a midpoint is too big or too small? No. Okay, turn the page, please. We're going to do the very last one, and then we'll do a little bit of your homework. Okay, very last one. Sure. That one? Okay, look at the last one. Okay, it says my car accelerates for 24 seconds. It accelerates in miles per hour per second. It's measured every 3 seconds. Okay, approximate the speed of the car using a midpoint sum with 6-second subintervals. Okay, what if it's a midpoint sum? Why are they going from 0 to 6? So that you have a what? A midpoint. So I'm going to go 0 to 6. What's my midpoint? 1.7. Okay, then from 6 to 12, what's my midpoint? 2.1, right? Okay, then from 12 to 18, 0.3. And then from 18 to 24, 1.1. Now notice that since my delta x is the same every time, I can pull it out to the front. What is the space between my x values here? 6. Very good. 6 seconds. So I would pull my 6 out to the front. 1.7, 2.1, 0.3, 1.1. Okay? And then if you integrate acceleration, what do you get? Do you remember? What's the integral of acceleration called? Okay, so let's write that down. 0 to 24, a of t dt represents the number of, now what would my units be if it's miles per hour per second times seconds? It would only be my seconds would cross out. It'd be the number of miles per hour that the velocity changed. Over 0 to 24 seconds. Okay, so acceleration, if you integrate it, tells you how much the velocity changed. Just like velocity, when you integrate it, tells you how much the position changed. Okay? Alright, so take a look at your homework. And I'm going to have you do number, let's do 3. Okay, take a look at number 3. Notice number 3 is one of the only ones that doesn't have a table. That's because you're going to have to make your own. Okay, that's why we're doing it together. So it says t is given in seconds. The velocity of the particle is given by v of t equals 1 plus t squared. Okay, then it says using a left Riemann sum, each interval will be 2 seconds long. Approximate the distance traveled. So set up a table. What is my starting and ending point from 0 to when? 0 to 6. And then how much do I want to go up by each time? What's my delta t? So 0, 2, 4, 6. Okay, then on my v of t side, instead of them giving me the numbers, they gave me an equation. So if I plug in 0 to this, what is 1 plus 0? 1. Okay, now let's do 2. Ready? It'd be 1 plus 2 squared. 1 plus 2 squared. Oh, wait, hold on. Yeah. 1 plus 2 squared. How much is that? 1 plus 4 is 5. Okay? Next, we're plugging in 4. So it'd be 1 plus 4 squared. Well, that'd be 1 plus 16, which is 17. And then for my last one, 1 plus 6 squared, that's 1 plus 36, which is 37. Okay, now set up a left endpoint for me, or a left Riemann sum for me. So I would put the integral of v of t from 0 to 6 is approximated by, what is my width? Is it changing or the same? The same. So that means that if all of these are a width of 2, I'm going to pull my 2 out to the front. And then on a left Riemann sum, who gets skipped, the first or the last? The last one. So it'd be 1 plus 5 plus 17. Now, if you want to say, this is 2 times 1, this is 2 times 5, this is 2 times 17, that's not wrong. But if it had multiple intervals, that would be pretty annoying, right? Okay, go ahead and do number 4, right Riemann sum. Okay, so it says it's in gallons per minute flowing into a lake. Use a right Riemann sum with the 5 subintervals in the table. So I'll go 0 to 60, r of t, approximated by. Then for my first rectangle, notice, are the delta x's the same or do they change? Okay, then change, there's no shortcut. So from 0 to 10, how far is that? What's my width from 0 to 10? 10, and then which is my right endpoint? Which one's on the right? 400. Plus, next one, I'm going from 10 to 25. What's my delta x? How much did my x go up? 15. And which is my right endpoint? 350. Okay, plus my next one, I'm going from 25 to 37. How far is that? 12. And then who's my right endpoint? 280, right? You're just going in order? So it'd be 280 would come next. Okay, then from 37 to 46, how far is that? 9, right? So that'd be 9 times 200. And then for my last one, I'd go from 46 to 60, that'd be 14 units. And I'd use the right endpoint, which would be 180. And notice who never got used on the right endpoint? The 500, because it was the first one. Got it? Okay, great. Good job. And that homework's not due till next Friday. Only homework 3 is due tomorrow. Remember, we're on Pep Raleigh schedule. And you don't have school on Monday.
We don't?
Come on, you crazies. It's MLK Day. Yes, ma'am. Yeah, you can do all of that. And then, guys, hey, real quick, do not add these up. That's a waste of time. You don't have to do that. Just write it down and you're good. Yeah.
I got checked though.
Yeah, that's okay. We'll get you caught up. I've been recording everything pretty much every day, so.
That's good.